Alright everyone, welcome to the second video of the week of the Kangaroo Weaver bird with minimal surfaces. So here we're going to move on to the fourth example in this series, actually here. And you'll see I actually have a similarly configured with the earlier number 3, the poly surface example, except these are mesh surfaces. These are mesh surfaces, mesh planes that were drawn and joined together as a continuous mesh surface, or a continuous mesh. Okay, so that's the input, and we'll still work with this. We can still work with the original example from the third one and use that to modify. Okay. So obviously the B-rep is not there anymore. Also we already have a mesh, so these actually we don't need, and this as well. Okay, so up to here, because it's a mesh, we obviously find a mesh container for it. So here, and set one mesh and link that in, and I'll hide the mesh that's out of the way. Okay, starting with the mesh, obviously you can go straight from the mesh, because this mesh is already dimensioned more or less to like a good density that we want. And actually, if you want to draw your own mesh, you would basically go here, Polygon Mesh primitives. These are mesh planes, right? And you can set 10 by 10. These I think are 10 by 10. So when you draw them to a specific dimension, 10 by 10, these basically are the building blocks for something like that. And they are faces or planes that are 10 by 10. Okay, so this goes into there directly. We were at edges, there's nothing here that you really need to change, and these basically become your springs. Same thing, this gives us all the anchor points. So if you look at the naked points here, okay, these are all the ones that are on the edges, right? And these are the ones that we push into anchor points. Okay, and if you take this basically, and this is like a very abbreviated or shortened version of it, and the other thing that's missing here is geometry. So obviously remember from the earlier example that Kangaroo can work with native mesh geometry. So if you push that in, this is the output mesh. Let's run it, and you'll see that automatically or right away it will do that. And the minimal surface simulation is working. And so you'll see in a way, actually, if you have a mesh topology that's set up correctly already in the first place, it's actually quite simple, right? You need to get your spring lengths, you need to get your geometry, and you need to get your anchors, and that's more or less it, right? And in this case, because your anchors are basically the naked edges, naked points, that's all. That's all you need to get a mesh output. And we can, well, let's not bake it just yet. I'm going to pause this. And so if we're going to get fancy a little bit with the coloring of this, what we can do is actually find a way to apply mesh coloring to this. And this is actually something that will carry over if you try to 3D print it on, let's say, the Z Corp, which is capable of printing embedded mesh colors. Okay, so the idea is that we're going to try to grab each of these mesh faces and find their sort of vertice or center point on each face, and use that as a measure to color it, basically. So let's try, let's say, face. We want this face normals, which extracts normal and center points of all faces in a mesh. All right, so we do that, then basically I'm getting all center points on each of these mesh faces. And because these are center points, we want to deconstruct not a vector. We have to go up. Actually, let's just go to vector point deconstruct. So this is the point deconstruct, and it gives us basically these points, and it splits the XYZ coordinates. All right, so we're in this case, because this is actually going sort of in the X direction, what we're going to use is the X, and you could use either one, like X, Y, or Z to color it, but we're going to use the X coordinates of each face's center point. Now, obviously the color components, here params, input, gradient, this guy, under here, the gradient, and let's right click presets, and let's find the most colorful one possible, which is here. And so this guy, it needs basically a gradient range, like basically the top or the bottom value and the top value, right, the min-max values. So we want to know what the min-max values for this X basically is, right? So the really easy way is to do this, bounds. Creates a numeric domain which encompasses a list of numbers, right? So it takes your values and says your minimum value here is 3.2, your maximum value here is 22.4, whatever, right? So it looks at all the values in the list and tells you what your largest and your smallest numbers are as a domain. Now, because this is asking for a domain, whoops, I'm going to do that, we will have to decompose or deconstruct the domain here. And you can find it obviously maths domain, deconstruct domain, same thing. Give it that. The start is the smallest number, the end is the largest number, so this goes there, this goes to there. Okay? The t value is basically your input, right? Where essentially it's all the x coordinates that you're going to measure this against. So this x goes into here. Now this hasn't really colored anything yet. I'm going to hide that. So we will actually need to use a coloring component. Let's see where it is. Mesh, utility, primitive, oh here, mesh colors. Okay. So the color goes into here, and your mesh is drawn from the output mesh here. And you will see that basically if you look at the color gradient here, on the low end, these are where the x values are the lowest, and here where is your x coordinate value is the highest, right? And it basically takes the mesh and colors it accordingly. Now obviously you could switch, you know, the x to the y, so low to high, or whoops, you know, sorry, if you're looking at this way, or z, and it will color it differently. But at least in this case, it's better kind of distributed in this direction. You can understand a little bit better. So these are all the faces that are lower in the x coordinate. Okay, so that's just like fancy coloring. You can bake it, bake the mesh. Just right click, bake, say OK, and you will see it comes in with color. Yep. Now, before this step, or somewhere in between this step, you want to take the mesh even and do the Weaverbird thicken. Weaverbird mesh thicken here. You could. Now that's way too thick, right? So distance, what is it set to? 5.0. Set number 0.3, for example. Okay, so that actually gives the mesh thickness and color at the same time. And you can change these 0, 1, 2. But if you bake that, then you will get basically a thickened and colored mesh that actually would be ready for the 3D printer, because you should be able to get a volume off of it, and it should be watertight. Okay, so that's number 4. I'll delete that because that might be a little bit heavy. So let's move to actually number 5, which is just actually a variation of this. If you show, let me hide the mesh color. If you show the geometry, you might have to show this back. So the input mesh is the same. The only difference here is that I'm trying to show, so this is exactly the same, I just wanted to kind of show you here. The only difference is I want to try to show how you are able to pick and choose basically certain boundaries or certain points that you want to manipulate, right? So given that original configuration where the result is sort of like that, right? So let's say, for example, in this here, I've pre-drawn an input curve. And let's say instead of having this mesh be constrained to, this sort of square edge outline, I want it to be constrained to this circle, right? Because with the normal mesh construction input, like there's no easy way to like make this go from a square to a circle, right? It's really hard to build. So what you can do is what's called the pulling sort of command, or the pull curve pull component to deal with that. Okay. So if you go to Kangaroo, again, under forces, obviously, there is one called curve pull. Constrain or pull points to a curve. So we do that. So this is basically its own different force object, right? So it asks for a curve to pull points to, which is that one, obviously. So let's put in a curve container and link it in. Okay. So this is the curve. Now the points that we want to pull to are essentially, no, not that, but to kind of show you, are these guys, right? The ones that are on around here. But in here you have actually all of these as well, right? In this this list. So we have to basically find a way to separate all out of this and just select these guys up there. Okay. Now there is a manual way to do this. You can basically bake all of these points out like this, and then plug them back in, basically, and only just like manually select those points and plug them back in. That's a little, bush league. So what we want to do is actually find a logic that works this way. So to do that, the first thing you want to do is, let's see, we want to be able to visualize things. So I want to grab the point list component that lets me visualize the numbering scheme, right? So points go into here, the size, set number, the scale here is around that, so 0.2. Okay, so now I can zoom in and I can see the numbering scheme here on all of these points, and actually it's probably starting somewhere here, right? 0 is there. Okay, now I'm most concerned with these guys, just these guys. So if I look at the numbering scheme here, let's see, it starts at 120, 129, goes all the way 139, 149, 159. So the largest, it looks like, let me delete this, get it out of the way. So the largest number here Smallest number is 120, largest number is 159. Okay, so that's the range. These are the indexes, right, the address of the point that we want to grab and push into here. Okay, so the way we do that, go to sets, list, and here, sublist. Extract a subset from a list. Okay, this asks for the list, base list, a domain of indexes to copy, and remap indices that overshoot the you don't have to worry about that. Okay, so here the list obviously is the whole naked points list, and the domain, which goes from 120 to 159. Okay, now there are two ways you can do a domain. You can actually construct a domain like this and do the text box 120 and 159. This is the explicit way, and you can see this happen a lot. Like, there are normal ways of doing this, explicit way of doing this. So this is basically, and you see it when I highlight it, actually picks those points out for me, right? That means I've gotten the right points. Okay, so this goes into this here indexes, this list goes into there as points. Okay, that's one way. The other sort of quick and dirty way is actually to do, say, 120, or actually do a text box 120 to 159. That when you do something like this, this is actually understood by Grasshopper as a domain as well, and so it works exactly the same way. So it's up to you, like, whether or not you're going to be changing this. This is just a sort of shorthand way of specifying a domain in text. Okay. Then the last one here is strength. I'm actually going to 0 to 5,000, and this is just by experience. All right. So this is the force, so we'll have to add this into the force objects, and you automatically you'll see an error come up, so you'll have to flatten the force objects for it to work correctly. Okay, and let's see, let's work our way down. Anchor points. So now we also have a separate problem. The other problem really is the fact that our anchor points here still actually include these in there. So if you try to run the simulation, let's see. If you try to run the simulation, it'll work, but this is still constrained because we have still set as anchor points. Okay, so what we need to do is we need to take out basically these points that we found from this subset, right, from that original list. So there's a really, really simple, easy way to do this. Under set sequence, let's see, call index, the first one. So this basically takes out, right, call, does remove from the list a certain index, right, items with a certain index. Now we already have the indexes, they're right here. These are the indexes of the subset items, right? So this goes into the index, this goes from the naked points, and this list, as you can see as I highlight it, is basically everything except for those, right? All of that original naked points except for those. So we replace this into the anchor points. And now you'll see that top edge actually start to kind of pull towards the curve that we drawn earlier. And that can be any curve, right? It can be a wiggly, squiggly line, whatever. Okay, and you'll see that I can adjust basically the strength of it to get it closer. I'm not sure how far this can go. Maybe you can get up to 9,000 or something. But it will get closer and closer to basically based off of the curve pull strength and how high this goes. It'll pull it closer. Okay, so that's actually how you set up this sort of curve pull situation. If you have multiple, then you basically need to have a couple of these and find their specific, grab them out as their individual bags, and you will be able to kind of do them individually. Okay, now this is the I would say the fancy version of kind of doing this boundary pull. Like I said, there is a sort of quick and dirty version where essentially you take a point. Let's move these down. Okay, and instead of, let's say, just looking at the naked points, I'm actually going to do this time to kind of show you. I'm going to do the closed points. Closed points are all of the points that are on the inside, right? And what I'm going to do is actually I'm going to bake them onto the default layer, which allows me to select them, right? And then I'm going to take these again and actually set a couple. So let's see, I'm going to pick a couple here and there. I'll go with 3, right? Right click, set multiple. Okay. So these are my points that I'm putting in, and here very simply what I'm going to do is I'm going to add them into the anchor points. Remember to flatten it when you have multiple inputs. So we start it. Okay. Let me hide all this stuff that's in the way. Okay. So these are the 3 points that I've selected. I should probably try to hide everything else. So I'm going to invert the selection and hide all that. Okay. So basically, I'm taking all those points, pushing it, baking them, picking a couple that I want, pushing them back into the anchor points. Let's see what happens. All right. So the ones that I've picked, right, these guys that are anchor points are now, anchor points that are in the middle of the closed points, right? So you can actually single out specific ones and pull them out as anchor points by themselves. Let me hide all this. Okay. Now, what you ought to also do at this point is you can actually drag and manipulate them. Just like that. Right, and you'll see the overall solution update accordingly to your modifications. Right? Now there's one thing, one caveat to this method though, is that once you reset the solution, these points will be flying off in space and they will actually no longer be part of it anymore, right? Because they're not lying on one of the original mesh points anymore. So if you need to kind of redo, then you actually have to undo your move commands in the Rhino viewport, so they actually do kind of lie on one of the original mesh points. They coincide with one of the original mesh points for this method to work correctly. Okay, so that's a big caveat to this method. All right, So you'll find most of these in their working conditions here. That's 1 through 5. And that just kind of gives you an idea of how some of this works. All right, that's it.